You know how to write code. You know how to containerize it with Docker. And you know how to push it through an automated deployment pipeline. When you're building a web shop on your laptop, this setup works flawlessly. But it works flawlessly because it only has to serve one single user, you. Picture what happens on launch day. When thousands of users hit that application simultaneously, your local hardware chokes. Requests time out and orders are dropped. You hit rigid physical limits. Your local CPU and memory cap out. A minor power outage takes your business offline entirely. A customer in Australia waits 8 seconds for a page to load, simply because the physical distance between them and your hard drive is too great. Meanwhile, you're paying for all that hardware even when it sits idle in the middle of the night. Transitioning an application from a local environment to Google Cloud Platform requires solving these exact constraints. You have to move away from relying on a single, fragile machine. The physical laptop is a bottleneck. To survive real-world scale, we have to stop buying hardware and start renting distributed computing power over the internet through abstract software APIs. The cloud is just a massive network of global data centers owned by hyperscalers like Google, Amazon, and Microsoft. You interact with these physical warehouses of computers entirely through an API. This matrix shows what you manage versus the cloud provider. On premises, you maintain every layer. With IaaS, the provider handles physical hardware and networking. With PaaS, they also manage the operating system and runtime. Your only responsibility is writing application logic and managing your data. But even with the provider managing the infrastructure, the physical location of your code still dictates how fast your users get a response. Distance dictates latency. To solve this, Google Cloud organizes data centers into regions close to users, containing completely isolated zones. Multi-zone deployment is the reliability standard. If one data center loses power, others instantly take over. By utilizing a PaaS model alongside a multi-zone deployment, you completely remove hardware maintenance from your workload and eliminate the risk of a single physical point of failure taking down your system. When you first build an application, you naturally write a monolith. It is a single codebase deployed all at once. Early on, it is fast to start and easy to reason about. A monolithic e-commerce application tightly packs users, cart, and payments into one block, sharing one massive database. As teams scale, developers step on each other's code. A small change requires redeploying the entire system. This creates an enormous blast radius. A minor bug can crash the entire application. Microservices solve this by separating capabilities into isolated applications, each with its own dedicated database and independent lifecycle. Because the databases and deployment pipelines are independent, the shopping cart team can ship updates 10 times a day without ever touching the payment service. But you should never adopt microservices on day one. They are a specific solution for organizational scaling problems that a brand new project simply does not have yet. Splitting a codebase prematurely creates a distributed monolith. You inherit all the severe network latency and debugging difficulty of microservices without gaining any of the independent team velocity. Slicing a monolith resolves the bottlenecks of a large team, but forces you to manage the profound complexities of a distributed network system. In a distributed cloud environment, infrastructure is ephemeral. Running instances will die without warning, and the platform instantly spins up new ones to replace them. Code written on a stable local laptop will crash in this chaotic environment. To survive, the software must be adapted using a strict set of rules, known as the 12-factor app methodology. Rule 3 focuses on configuration. Hard-coding passwords or API keys is a major vulnerability. Those credentials must be pulled out of the code entirely and injected at startup using secure storage, like GCP Secret Manager. Rule 6 dictates how processes run. Cloud applications must be strictly stateless. Any data the app needs to remember, like a user session, must be pushed to a shared external cache to survive container destruction. Rule 11 applies this same logic to logging. You cannot write log files to the local disk. Applications must write logs directly to standard output, allowing the platform to aggregate data centrally and survive crashes. Adhering to these 12 principles ensures that every instance of your application is interchangeable, disposable, and entirely resilient against network chaos. With the code adapted for volatility, it has to be physically moved from your local machine into the live cloud. This requires a strict automated build pipeline. Pushing code to a Git repository triggers Cloud Build, which packages the application into a container image. That image is stored securely in Artifact Registry and then deployed as a stateless process on Cloud Run. By breaking down the monolith, these newly deployed Cloud Run services are entirely isolated. To function as a cohesive application, they must communicate with each other over the network. The first method is synchronous communication, using protocols like REST. Service A calls Service B and stops, waiting for an immediate answer. This should only be used when immediate data is required, like validating a login. For fire and forget tasks, use asynchronous communication. Service A drops a message into a pub sub-queue and immediately resumes work. Service B retrieves it later. The queue absorbs delays, preventing cascade failures. A robust cloud-native architecture separates deployment into strict automated pipelines and isolates running services through asynchronous messaging to prevent network traffic from causing system-wide delays. When traffic spikes, the application must scale. True cloud elasticity is predominantly a horizontal operation. It means reacting to load by running more copies of the application rather than just building one giant machine. In environments like Kubernetes, the base unit is the pod. When a traffic surge hits, scaling operations begin. First, the horizontal pod autoscaler monitors requests and automatically adds more running copies of the pod to distribute the work. Simultaneously, the vertical pod autoscaler assesses constraints, adjusting memory and CPU allocated to individual pods struggling with heavy tasks. But there is a ceiling. Eventually, the underlying physical machine runs out of computing space. When pods can no longer be scheduled due to lack of room, the cluster autoscaler engages. It provisions entirely new hardware VMs, expanding the physical footprint. Understanding this hierarchy provides a critical debugging heuristic. If you observe that your new pods are stuck in a pending status, the infrastructure layer itself is full. You have to check the cluster autoscaler first, because the system physically has nowhere to put the new application copies. True cloud-native scaling is a multi-tiered horizontal operation, continuously optimizing process counts, internal resource allocations, and the underlying hardware nodes. We began with a single monolithic application running on a laptop, bound by physical hardware limits. Now we have a globally distributed web of microservices. By utilizing cloud primitives, managed data centers, and automated pipelines, we solved the constraints of hardware capacity and development gridlock. But we traded those physical limitations for distributed network complexity. Making this architecture function requires strict stateless design, robust messaging queues, and multi-dimensional scaling mechanisms. The local host environment has been completely transcended. You are now equipped with the underlying logic to engineer resilient, scalable systems out in the cloud, exactly where